right, howdy. So we are here again. Another question to work on, to look at. So actually, I had some time to look at this question last night, and not just last night, but I realized after trying to solve this problem, I realized that I did not actually have the solution. Let me see, did I submit it yet? No submissions, okay. Yeah, I didn't actually have the solution yet, so not quite, like, all of this is all well and good, but not exactly the answer, right? So the answer is a little bit more complicated. It's not too bad. It's the same idea, but I did a little bit of math to figure things out. So I'm going to try to implement what I came up with. And I think what I came up with is correct. I do believe what I came up with is correct. It's maybe not simple. It's relatively simple, but it's definitely correct, I think. Or not definitely correct, but I think it's correct. Not entirely certain though. Yeah, so let's see. There is one issue of there is one issue. We do need to handle this edge case actually. So let me see. Okay, so we can get rid of this edge case. I'll explain what the solution is going to be in a moment. We're going to rewrite this to k also instead of total. So order stat, we still want this routine a, b, k, and there's nothing really to debug at the moment. So we have a certain index we're looking for. Left, right, mid, med, far right, far left, which array. I don't think we need the far left, far right anymore either. Let me think. Do we? I don't think so. Well, we might. Do we need that to calculate the larger and the smaller? Yeah, we do. Actually, we do need this. Okay. Pointer to the constant pointer to which array? Yeah, that's fine. We do actually probably want that too, so that way we have a like a way to access the array that we're interested in for a particular range struct that we're operating on. It's sort of like a, instead of calling it a range, we call this like a I guess you call this, by the way, we can make these well, no, yeah, we can make it, yeah, it's fine as a struct. So you might want to call this like a like an array view or something like that. Range, I don't know, call it range. Yeah, it's fine. Range is fine. All right. Total smaller is index. Total larger is the total minus index plus 1. Yeah, that's fine. And the total is going to be target. It's not. We're actually changing the name to target larger and target total because that's what I was using before, and I was kind of mathing it out exactly the answer here, or not the, yeah, roughly the answer here. So we have alpha, beta. These are fine. Take the midpoints. Actually, what you're going to do is you're going to say check whether one of the ranges are empty. So if so, terminate with the correct answer, final answer. So this is the key. This is what I was missing before. So if alpha dot left is greater than alpha dot right, or beta dot left is greater than beta dot right. So the deal is we're going to say, depending on which one's sort of greater, we could say, so we would say if, so we do a check bool check equals alpha dot left is greater than alpha dot right. So if check, it's two checks. Else, so it's either the first one or the second one. So if it's the first one, so what we're gonna do is we're gonna set range and const range x and y aliases, and we're gonna start with pointers. So x will be initially alpha, and y will be beta, const pointers. And then if check, then we're gonna set potentially swap x and y. So what we want to do is we want to make x the range that we're going to process. So start with alpha and beta, and we swap if check happens to be the one. So if not check, really, if it's not check, then we're going to swap x and y, and so that way, so if so actually no, it's the other way around. It's a little confusing. So if alpha is the one that's empty, then we want to swap x and y such that x is pointing to the one that's not empty. If alpha is not empty, then that means we're correct. Alpha is the one we want to start with. So we can do it this way, and then we can say, I would just call this like R1, R2. It's fine. And what we want to do is then take const range reference x, and that's going to be dereference R1, and range y is then dereference R2. Okay, there we go. So that'll give us what we're after. Now we would say, actually there's something important here. It's so y is pointing to the range that's gone. So we'll say int smaller elements is going to be y dot left. Yeah. So the left and right crossed. Now the left is actually going to tell us how many elements we need to remove, how many elements that the range that we still have, how far it is into our sort of total. If we merged both sorted arrays, this amount will tell us how far in, or actually how many elements are smaller than that range. Hopefully that makes sense. But yeah, that should be the result after our processing, which I don't really have a proof of that, but I'm fairly certain that's what will happen. So now we can say return. It's going to be x. So we'll say now if we have check and beta left, you do check 1, check 2. There's a tricky thing that happens here also. Check 1, check 2. So you could do check 1 or check 2. And I'll explain why we're doing it this way. If check 1 and check 2, if both of these checks fail, throw an exception as the desired median doesn't exist in the lists. This should not occur. Should not be reached. So this can technically happen, but it shouldn't, as if you're using using this properly. This actually is not it's a runtime error, but so median out of range. possible range. Target median not found. Target order statistic not found. Yeah, so this shouldn't actually happen. Assuming that doesn't happen, then we can try this. So this is going to be the smaller elements, though. Actually, what you're going to return is going to be x, the x range. You're going to get the which array, which is now a pointer to an array. And we're going to process. We actually just dereference this. We dereference this array. And now we're actually going to access the array. Where we're going to access this is going to be the way it goes is the target smaller minus the smaller elements. Or sort of, we'll just say S, already processed, or just S, yeah, or other elements, I guess, or just, there's also const. Oops, what would I mean to do that? Oh, what happened? Small found, I guess. Yeah, basically these are the smaller elements we've already found in the other array. So the target smaller, if we want like 5 smaller elements, then we want to take, if we already found 2 in the other array, we can only have to go up to index 3 to get 0, 1, 2, 3. So that's how this works. So it's kind of a trick at the end here to exit the loop. And yeah, so I mean that's kind of it actually. That's like the key that we were missing before. There's also one slight change here too that we were also missing. Okay, we can leave that. So here we don't need to do this. Compute counts. We did that correctly the first time, I think. There's sort of smaller and larger values. We actually don't need to do all of this. This is excessive. So we can do. There are a few things actually. Also, there's even and odd cases are fine. What we're looking for now. So there's actually updates you can do to each range. That's kind of simplifies all of this. Actually, the math goes like this. So we go here. So we have, let's just say like A1 plus A2 plus 1 represents the smaller elements, where A1 and A2 are the mid values of each array, or the indices into each array. Current indices in each array. Smaller elements, yeah. Larger elements are the difference between the total. The smaller elements can compute the update to each A1 and A2 can be computed relatively easily. As follows. So yeah, that's kind of what's going on here. And we could say like alpha. I like to use alpha, but alpha 1, we already use alpha and beta, so we could use like what's an easy one? T, N, I, J, K, L, X, Y, Z. Let's do Z. Z1, Z2. So yeah. The update to each of the left and right, new left and new left, and new right range values, relatively straightforward. Compute the Z1, Z2 values computed again from these new range values. Be continued. So one issue is actually these are, it'd be mid 1, mid 2, mid 1 plus mid 2. Oops. Okay. So we don't actually need to do all this other stuff down here. Not really. So we can do smaller. Say small. It's going to be alpha.mid plus beta.mid. So we do actually need to figure out which one's which though. This modify ranges. We are going to do that sort of. This part we need to do. Oh, the swapping thing that we do, not thing, but the swapping that we did before. Yeah. So we do need to figure out swap the arrays such that the X range is referring to range median value less than or it has a target value or a current value index valued lesser value. The other ranges current index value. Can be greater than equal. The greater range can have a value at its current index. It's greater than or equal the X ranges. Current index value. Yeah, it's a confusing concept. I don't know if that's like very well articulated what I'm describing there, but this should be okay. So, so can we not? I think you could swap actually the const range pointers, but actually we're actually not going to modify anything in this part, so we can use const, I think. But in this part, we are going to modify things, so it's not going to be const. So T1, T2, alpha, beta, depending on which one's larger. So it actually, yeah, if alpha is larger, then we'll swap it. Although if it's equal, we won't swap. Doesn't matter if they're equal. Yeah, and then you update x and y. Okay. So now we can say small is, we'll do x and y, so now they're in the right places. X mid, y mid, plus 1. Constant large is going to be k minus small, where k is the total number. We're going to say constant new left. New left is going to be the current left, which is x dot mid, minus standard max, which we also want algorithm here. Yeah, we do. We have that. Exception vector tuple. Yeah. Okay. I don't know if we're going to use tuples at all, but that's okay. And we're going to have -1, and where that -1, the reason for that I'll explain in a minute, but, well, actually I can explain it now. So we're going to do target. Now the left is, I think it's target smaller. So our new left, we move over from the left side based off of how many things are larger. So it's the target larger minus large. And the new right, we move on the other direction, and y mid, and it's going to be target smaller minus small. And actually the large is, right, we said k minus small. Yeah. So this is kind of nifty. So and it's plus this one on the other side. So what's going to happen is the two medians are going to split our elements into 4 pieces. So there's the left side and the right side of x, and the left side and the right side of y. We reorient x and y depending on which median is smaller. If they're equal, it doesn't matter where they're oriented. And then we figure out how many elements are larger than the left side of the top array. And those are both going to be all the elements to the right of both sides. And then that's the large part. And the smaller part is the other way around. It's that all the elements to the left of both medians, and we're going to use those to figure out how many of the largest right most elements. So the second array, the largest ones, how many of those we can eliminate. And a good portion of the time, you'd eliminate all of them. So you'd eliminate half the elements. And this is how you calculate that. That's what's being calculated here. We basically figure that out by, I think, we assume the second element is larger than the first. The second median is larger than the first median, and so that sort of math works out there. It's kind of involved to explain that. I'm not going to explain it, but we'll just say like there's a sort of target for a particular order statistic that we want. There's a target number of smaller elements and larger elements where that's positioned, and we're going to use those numbers to eliminate half of the elements at each iteration. That's like the basic idea to make this logarithmic. Now what we can do is also the -1 is there because in some cases you don't want to loop infinitely. You do want to eliminate one element. So in some cases you just eliminate one element at a time, and that's what that -1 does. Like you can't eliminate more than that because you don't actually know where the elements that are further in each direction, where they're oriented with respect to each other. So you can't you can always eliminate the middle one, which is what the -1 is, but you can't go further than that. That was a sort of mistake that I made the other day, is that I kind of assumed you could actually eliminate even more elements in each iteration. So this will update your new left and your new right for each range. So x left is then updated new left, and y right is then updated to the new right. So the new left and the new right is, if you imagine there's a left and right on each range, we're pushing in those ranges, right? The right side on the y part and the x on the left side on the x part. Both of those are getting pushed in, and then possibly they're getting rearranged and pushed again, and so yeah, do that kind of thing. And you keep doing that until this occurs up here, where one of the ranges disappears. Eventually, one of the ranges disappears, and you can calculate where in the other range we need to be. And I think that's it. I think it's actually that simple. All this stuff we don't need anymore. Yeah, that's pretty much it. Pretty much it. And then here we said, yeah, we'll throw. Oh, actually, there was a throw here I wanted to keep. Or stat not found. we actually can't exit this loop without sort of breaking down one of the arrays. So this could loop infinitely too, but we're not gonna mess around with that to try to make it loop correctly. So yeah, save your order stat. Now I think this works. I could be wrong, but I think it works. And then there's even versus odd cases. If it's odd, you take just total minus 1 over 2. That should be fine. Order stat. If it's even, then you have these different values. You don't actually need this debug information anymore. You can just return a plus b over 2. Yeah, that's fine. So you could do order stat A, order stat B is just x, and then x plus 1. Yeah, those don't change either once we set them. So, right. Okay. What does this do? Oh, yeah. We're using k now instead of total. We kind of went over that before. Let me just take these test cases. Let me also pause for a moment to yeah, okay, chat, everything looks okay. Just want to make sure I don't have anything incriminating here. That's up. Let's see. Should actually get probably more test cases than this. Runtime error. Oh no. Uh-oh. Uh-oh. Also want these test cases too. Want all of these cases. So these fail, and why is that? What is the issue? So again, I could be wrong with this algorithm. Hopefully not. Which one causes the error? That's what we want to find out. It's not the first one. Okay, is it the second one? It's not the second one. It's got to be one of these two at the bottom. Is it the first? Is it the one above? It is indeed. Okay. What about, does the other one have issues? They both have issues? That's interesting. So we're pretty close. Almost got it. Almost got it, seems. But some mistake here, somewhere, somehow. All right, runtime addition. So, or runtime error. So what happens? Let's debug. Okay. Alrighty. Let's just see where these values are at each iteration. We'll just say alpha left is alpha left, and then we'll say alpha right, and then we're going to say beta left. Yeah, we'll put them all in one line. Beta left. And finally, beta right and beta right. Put that all on a new line. Or put that, yeah, put that on one line. All right, so this is really interesting. What did we do? So we had 0, 3 to 0, 14, right? So beta, right? Alpha, there's alpha and beta, right? Alpha gets reduced to 0, 1, beta gets reduced to 8, 14. So we would start at 34, and the other one would be, what's this? This is, we said it's 15. And also this is, let's see, 15 plus 4 is 19. So it's 19. So we don't need to do, it's not even, right? It's an odd number, right? 4 plus 10, 11, 12, 13, 14, 15. So yeah, 19. So we have an odd number, which is great, or which is okay, I guess. Odd number. So pick the middle of both. So 34 is here, and then we said this is 15. So there should be the 7th. 1, 2, 3, 4, 5, 6, 7. 7. There should be 7 on the other side. 1, 2, 3, 4, 5, 6, 7, 8. Excuse me, 8. Oh wait, there's 16. No. How many of these are there? It's 10, 11, 12, 13, 14, 15. Yeah. Okay, it's 15. So half of 15. So the 7th index, which is actually the 8th element, 1, 2, 3. So it's actually 8. So there should be 1, 2, 3, 4, 5, 6, 7 on one side and 7 on the other side. Yeah. Okay, there we go. So pick 34 and 8 to start, and clearly this one's larger. So this becomes y. This becomes x. The new left that we calculate is what? We said it's exactly this calculation here, right? So it's -1 maximum. So its current position, which is 7, and we subtract. This could be -1, or this could be target larger minus large. So yeah, we're looking for all of the number of things that are larger. So we have 7 here, and we have 3, so 10. So we have 10 larger values. The target larger, we said, is going to be, target larger is going to be k minus index plus 1. Target smaller. So we said the index into 19 is 19 minus 1 over 2 is 9. So the index is 9. So 9 elements that are smaller, and then there should be, is that right? 19 minus 1 is 8. 9 elements that are smaller and 9 elements that are larger? Yeah. 19 minus 9 is minus 9 plus 1. 19 minus 9 plus 1 gives us 9 as well. So you get 9 and 9 for target smaller, target larger. 9 and 9. Okay, that's all well and good. And then the large number of elements, we said, is just k minus small. K is the 2 indices added together plus 1. So we have 0, we have 1. Plus, we said this is 7. 1 plus 7 plus 1, it's 8, 9. So 9 is small. So 9 minus 9 would be 0. So for this new right, we would get 0. For the new left, we would get, the target larger is, actually it's 10, because, or large is 10, because the total is 19, and we subtract 9. So we get 10 here, but target larger is 9. 9 minus 10 is -1. So actually we would shift over to here. So we would shift over to the new left after the first iteration should be not 0 to 7, but it should be for beta left should end up at starting at 8, so 8 to 14, which I think is what we got. Yeah, that's what we got. And the new right on the other side, trying to figure out how many things are smaller than these two on the right side, 56 and 70, which I think both of them get, I think all three of these get eliminated, right? Or no, yeah, both of them get eliminated. So we end up with how many things are smaller? We said was 1 plus 7 plus 1 is 9. Yeah, we get 0. So actually, yeah, we just end up both the right sides get eliminated. So we end up with 0, 1, and 8, 14. Yeah, that's exactly what we expect. But then, so now we're looking operating on this range and this range, right? So here we would pick 23 for the midpoint, and the midpoint here, there's 1, 2, 3, 4, 5, 6, 7, 8 elements here. So we would get this one, 10. So now 10. So now this is on the smaller side, and this is on the larger side. And we would say how many elements. Now somehow we end up with, I don't know how we get alpha left is -1 and also alpha right is -1, and I don't know what happened there. Or -2. How did alpha left go further to the left? That's not supposed to happen. What happened there? What's going on? So, all right. So what happens to this calculation now? So we have 10 and 23. So now these are larger. These 23, 34 are the larger ones, or considered larger than 10 at least. It may be better to actually like calculate these here. Oops. All right, so we would lose these two, and the rest. I operate here, and we say we get small is 0 plus 0, 1, 2, 3 plus 1 is 4. Large is then we had 19, I think. So 19 minus 5, 4 is 15. Actually, no, this is wrong. I did the other way around. Sorry. You have to actually keep the same indices that you had before. So this is this index here is 0, 1, 2, 3, 4, 5, 6, 7. So 7, index 7. So small is 7 plus 0 plus 1 is 8. And then large is then 19 minus 8 is 11. So to the right of 10, there are 1, 2, 3, 4, 5, 6 things that are larger. Wait. It's 1, 2, 3. It's 1. No, 10 is smaller, right? So 10 is on the smaller side. So it's 1, 2, 3, 4, 5, 6, 7, 8. What? That doesn't seem right. All these 4 plus, all right, because those are larger, plus 1, 2, 3, 4. That's only 8 elements to the right that are larger. I guess it should be, so small should be 10, and large should be 8. What happened? How do we get this? Maybe the large calculation is slightly different. No, I don't think so. I think it's exactly the opposite. It's like the inverted. These two, when you add these together, should actually be, I think you should add these together. You should get 19. You should get the total, right? 10, 11, 12, 13, 14, 15. Yeah, 15, 19. It should be the total. I think we add these two. So just the way that they're calculated. So the larger one. So this actually is on the bottom because this is still larger. And have 7. So 7 is this index. You have 8 elements to the 7 elements to the left. What are we thinking here? So there's like 2 elements to the right here. So my thinking is small. We said just alpha 1 plus alpha 2 plus 1, which is 7. 7th index plus 0 plus 1 is 8. So I don't think that's correct, right? The number of elements that are smaller than this 23 that we know about. Oh no, it is. Yeah, it's all these ones. And oh, excuse me, it's not 8. I'm sorry, it's not. It's 8. It's 8, 9, 10 plus 1 is 11. Yeah. Okay. That makes sense. That makes sense now. And then this should be 8. Okay. A little confusing, but right. So what we want is 8, 9, 10 because we're actually at this 10. It's actually 7. So this is index 7, 8, 9, 10. This is index 10 as index 0. So yeah. Okay. Okay. A little confusing. Yeah. So the number of elements that are smaller than 23 is it's all of these elements, right? These small ones. So 10, and then there's you make it 11, right? Because it's 7, 10, 11. Yeah. This one is where we're at. So it's 11 elements that are smaller because we know that we assume these are smaller, right? And so the larger ones that are larger than 23 then are the other elements. These are actually. So those are all the elements that are smaller than 23 and everything to the right of 23. And then the elements that are larger than 10 and are to the right, to the ones that are, all the elements that are larger than 10 and would be larger than the elements left of 10 as well. That's the other number. That's 1, 2, 3, 4, 5 plus the other 4, which is actually gives us 9, it looks like. Right. Oh no, excuse me. It gives us 8. Right. So it's 1, 2, 3, 4 plus 4 is 8. Yeah. And they just happen to be inverses of each other. If you just subtract the total, you'll get the other. Okay, that makes sense. So now we'll call it Z1 or just mid 1. It becomes, or not mid 1. So new left is then current. So mid 1, we'll say. Which is the one on top, minus, we said max of -1, we do curly braces, -1, and the difference between the target, larger, and the large, right? Now, for some reason, this gives us a negative value, I believe, or something like that. I'm not sure exactly what happens here. So TL, target large, is, we said 9. Target small is 9, and large is 8. So this becomes mid 1 minus 2. Okay. So now that's a tricky thing because 9 minus 8 is 1, mid 1 minus 1. How do we end up with negative? So mid 1 is actually 0 already. So the left, oh, I see. So the left could end up at, all right, so I think the issue is that we would need to go very far to the left. Oh, I see. Okay, I think I see the problem. So basically what this is suggesting, if we go negative here, um, this actually is fine. No, is it fine? The right side should actually go to the left slightly. I think that's part of the issue. Is that basically what this is suggesting is that that's really interesting. I don't know. I don't know what to do with this. What does that mean? Well, I know the median here is not going to be one of these four because these four are totally to the right. Or no, they're not totally to the right. They're actually I don't know what the median is here. What is the median for this? What's the answer? Let's start with that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 23, 34, 56, 70, 100, 100, 100, 100. So this is, so we almost have, we have the right idea, it's just not implemented correctly. I think we have the right idea. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And we said it's 19 divided by 19 minus 1 divided by 2 is 9, so index 9. So it should be 10. So this is the one, right? This is 10 is what we want. What that means is that this is totally to the right, but for some reason we end up with our left side going off. And the reason for that, it just means that the median that we're looking for, like we would, in order to eliminate, I think that's kind of weird. So in order to have enough values, I think what it means is that in order to have enough values, the target, yeah, so the target large minus the large amount. If the target large is 9 and we only have 7 to the right, that means that we only know about 7. That means we cannot necessarily eliminate anything to the left. In fact, the only things we can eliminate to the left are things that are smaller. So I think what we need to do is just make sure that wherever this ends up going, that we're trying to eliminate values, not necessarily, yeah, we're trying to eliminate values. So if we don't eliminate anything, that's really what this is supposed to be for. When this value is, when this is positive, so I guess there is actually another piece here we need to consider, is that we actually can't eliminate anything from this side. That's sort of the deal from this point in the algorithm. And that's kind of what I'm missing, is that like eliminating certain pieces. Like if you can't eliminate, if there's nothing to eliminate, because if the new left was actually, so really actually what we were expecting is the new left to come either be 0 or 1, not a negative number. It could be a negative number if those values exist to the left, but if they don't even exist, so I guess what you need to do is just check to see. You also need to make sure that this value, if you're moving the left, it needs to be greater than, well, no, it has to be, it can't go, this new left has to be in the array. I think that's what we have to check. It just has to be in the array. It doesn't actually have to be in the array completely though. It could be, could go off the edge to the right. It just has to, I think it just has to be greater than 0. Yeah, greater than or equal to 0. If it's less, yeah, it'll never be less than or equal to. So we can make this greater than or equal to 0. The new left, and the new right is similar. The new right has to be less than or equal to the rightmost bound. The new right will never go further than that. So yeah, so I think we'll just say the new left and the new right, we have to have extra bounds on where those are. That's a tricky thing. All right. So new left, new right, we'll just say standard max of 0, and new left, and then this has got to be standard min of y is far right and new right. It's really not 0, it's just x dot far left. Can't go, yeah, you can't, your new left can't go further to the left than the far left, and your new right can't go further to the right than the far right. I think that's the deal. I think if we do that, we'll be in better shape. I'm not sure what'll happen now, but I think that'll at least handle that one spot we were stuck at. Okay, there we go. That's correct now. All right, this seems to be the only issue that we had. All right, let's see how we do on a whole boatload of test cases. That's kind of a subtle thing, but yeah, it's not something I would have figured out like just thinking about it. I would have needed to go through some test cases. So we can get rid of the debug code now, I think. Are there other test cases we can come up with? Like, I'm not convinced that this is correct. I don't think this is right. Part of me just thinks like there's no way this is correct. Like there's got to be some test cases that we've missed that just aren't correct. But this is pretty good if it is correct. So we could do 8. Let's do some weird ones. Let's do 9, 10, 11. Let's reverse these two. Let's put like, let's weave, so the 1, 3, 5, 7, 9, 11 with 2, 2, 4, 6, 8, 8, 10, 12. We can kind of eliminate things a little bit here, and like we'll just put like 8 right in the middle, just one element. We can do something like we can get rid of 8 altogether. Like you try stuff like this, things of this nature. See how we do. Okay, that seems to work. I don't know. What are some of the test cases we could try? Well, I don't know. I mean, if these work, then it's going to be kind of hard for me to, I think, to find something that doesn't work. Let me do like, 1, 2, 3, 4, and then just like 8, 9, 10, 11, or just not, yeah, or just 10, 11, 12, 13, 13, and then we'll do, 5, 6, 7, maybe 8, 9. Could do like 8, 8, 9, and then 14. Oops, 8, 9, 14, 15, 16. Something like this, where they're kind of split level type of thing going on. I don't know. I can't really think of a test case that'll break this. I just don't know. There's got to be something that breaks it though. There's bound to be. Hey, we got it. Hey, we did it. Oh, all right. Not bad. Sweet. All right, that took some time, but we got there. Heck yeah. I mean, I should say I shouldn't curse, but we'll just say, hey, we get it. We did it. We did it. I'm going to change the name to solved. Hard, solved, and part 2. Yeah. I guess we ended there. I don't know. It's pretty good. It's pretty good. We did it. Figured it out. I knew I had the right idea. That's so tricky though. This is like so very tricky. It's very, very subtle what's happening here. We also use kind of a lot of data, I guess, a lot of memory. I guess you don't need that much memory. Some of these things I guess you can calculate once. Well, I kind of like, yeah, I don't know. I kind of like having the range objects and just kind of swapping them relatively easily. Let's see if we can get a better runtime though. I'm a little disappointed at the runtime. The runtime is super slow. Yeah, it's not as fast as it could be. My memory's usage is pretty good. Is okay. It's not 90%, but it's okay. I probably could reduce the memory a bit, but I don't know how I can reduce the runtime. It's probably kind of random how fast the runtime's going to be. I guess, yeah, I don't really know. I don't know. It's not doing that many calculations. Like it's pretty. It's pretty simple, the calculations. 73%. That's okay. I don't know. I don't know. We could make this faster. Can we make this faster? Is there a way? It's okay. It's okay. Huh. Do we need? We actually don't need these parts. These alpha med and beta meds. We can get rid of that. Optimize this a little bit. Alpha med, beta med. Alpha mid, we could say. I think that works. I think that works. Could try that. See if that still executes. Removed the one extra line. Actually, didn't really change it much, but yeah, a little less memory. That's good. Memory's higher. I'm pretty sure we can get 100% memory, optimal memory, but I'm not sure. I'm not sure if we can get better runtime on this. I know the maximums we can remove these variables, the max and mins. Like we can remove the functions and put like we could put like raw, sort of the raw functions, the like if else state. We could have branches there instead of functions. That could speed things up a bit. But otherwise, there's not a lot we could do here to change this. Not too much. I don't know. This is reasonable though. Yeah, it's okay. We got it. We did it. I'd say with LeetCode hards, it's like if you can get it at all, it's pretty good. But there's definitely like we don't necessarily the far left and the far right. We can just use. We don't need to keep that that memory. Definitely not. Could do plus small minus k here also for the large. This is minus k plus small. Put these over here. I mean, yeah, it's okay. I don't know. I like the swapping. I think that's okay. I think it's okay to do that. Technically, if we get rid of this exception, it'll be a little bit faster too. There's that also. Let's see. Yeah, we don't actually need this part. Oh wow, that's a lot faster. Look at that. And then you could say like, so check. You could say, not a lot faster, but it's a little bit faster. You could check, or the other one. Save a little bit of running time here. A little bit of memory, a little bit of running time. Hey, there we go. Beautiful. Gorgeous. Gorgeous. Don't have the best memory, but yeah. So we could reduce the memory a little bit further too if we wanted to. That's what I want to see. That's what I like to see. Almost 100%. Nice. Nice. Get 100% on a LeetCode hard is pretty good. It's pretty good. Yeah, I'm pretty sure if we replace these functions with branches, then these four, that tends to speed things up a little bit. I think we'll get 100% if we do that. And then also we could slightly reduce the memory even more by just removing some variables. Pretty neat, pretty interesting, not bad. But the basic algorithm stays the same. I think it's just like we were saying. It's the basic algorithm is the same. We basically take two medians of each array. We reorder the arrays based off which median is larger. We declare one x, one y, where x is the smaller values and y is the larger values, and then we can use that to split the array into two pieces. The left and so there's four pieces. There's left and right on x and left and right on y, and then we can usually eliminate about half of these elements by eliminating the smaller values on the left side. We can count how many larger elements there are on the right sides and add that up and say, if that's larger than the target number of, for our median or order statistic, how many we expect. If it's larger, we can eliminate those smaller elements on the left side. Same thing on the right side, we can eliminate the larger elements that have too many smaller elements on the left sides. So there's add the two on the left side roughly, and we get the smaller elements, add the two on the right side, we get the larger elements, and we could say certain elements on the bottom, on the y right side are too large, there's too many smaller elements. We can get rid of those, and then on the x left side, there's also too many, we have too many larger elements for those, so we can eliminate those on the left side. So what ends up is we get four pieces that we split into, and we can eliminate two of them, so we eliminate roughly half the elements each time. And I think the only time where you don't eliminate half is when you're getting kind of like closer, sort of quote unquote nitty gritty, where there's only a few elements to manipulate. And then at some point we end up losing the median altogether, and then we have a section that we know how many smaller elements there are based off of where we lost our other array, and then we can just index into the right spot in the remaining portion, the remaining array. And that's it. That's the whole algorithm. Pretty straightforward, actually, but it's kind of hard to understand it and hard to code it as well. And we said Z1 and Z2. We just said the mid 1 and mid 2 values. Really should be, yeah. Super interesting problem, and pretty interesting algorithm too. Interesting solution. So yeah, that's pretty good. I think we basically have the optimal algorithm here. We probably just need to like remove a few pieces. Maybe we could optimize it slightly, but I very much like associating all these different pieces with one array as well. So that way it's kind of easy to kind of manipulate between arrays. So we have just sort of one object that represents an array with different sort of important values that we're considering. This mid isn't really mid anymore. It would be like current is better than like the current index, because we're not really looking for the middle indices anymore. I guess we're looking for like any this will work for any arbitrary order statistic. So not just the median, but any position that we're looking for. But yeah, so let me go. That's pretty good. Thank you for watching. I appreciate it. I will talk to you soon. There we go. We did it. I almost can't believe we did it. I was so lost yesterday that like it was like hours I was spending on this trying to figure it out, or not figure it out, but I got coded it incorrectly. It really is like with programming, it really is like how much time you spend thinking about the problem matters a lot, because the longer you spend thinking about it, the better the design you can get, and then you can get the right answer instead of like some halfway not quite correct answer. Yeah, you definitely want to think about it. And also, I think I was kind of yelling in the microphone before, but yeah, you want to like spend as much time as you can thinking about problems, so that way you can get the right answer. And then coding, it's usually not too hard. That was an interesting one though. There were a couple of test cases there that I got kind of hung up on. That's a hard one. That's a tricky. I mean, I can see why it's a LeetCode hard. Like that's a tricky one. All right. So thank you for watching. Take care. I'm kind of debating whether or not like the volume should be higher or lower. I feel like the volume should have been lower, because I'm very excited and I'm like practically yelling in the mic, and I can see it going red quite a bit. So I guess maybe my volume should be lower. But super interesting. Yeah, I feel good. Like that was good. We did it. Like obviously it'd be better if I could do LeetCode hards in like an hour rather than like 5 hours, but That's pretty good. I mean, sometimes they used to take me like days. So sometimes it take me a long time. So I'm getting better, getting better. Like at some point I'll be able to just knock them out. That's a hard one though. That would definitely take some time thinking about it. I think it also like if I solve all the LeetCode hards, like it'll get to a point where I'll probably just like know all the problems, and then yeah, that'll be the end of that. That'll be pretty easy after that. So yeah, definitely like thinking through the problem seems to be the lesson here. Like think it through a little bit more before I start coding. I think that seems to be the right thing to do because the approach I took, I just like thought it was correct, it wasn't correct, and had to kind of. But I did have the right idea originally, though. That's the thing. The idea that I had at first was the correct idea. Was a reasonable. Was actually optimal. Actually, we had 99.85%. So we are optimal. But yeah. All right. Anyway, I'm gonna go. But yeah. Coming up with the idea and then like thinking through how it might be coded properly. Definitely want to take that time to think that through before you jump into coding. So yeah. All right. Thank you again for watching. Talk to you soon. Pretty sweet. We got it. We did it. Very satisfying because LeetCode hards are challenging. I mean, they can be really challenging. So yeah. All right. Take care. Have a good rest of your day.